Have you ever thought that one fine day you went to the nearest vending machine, bought a bottle of water, drank it, and thought,
Man, this water tastes like plastic.
then congratulations, you have just consumed microplastics. Okay, the tasting like plastic part was a joke, but still.
Did you know that in research conducted by the Faculty of Medicine and Health Science, University Putra Malaysia, concluded that the amount of microplastics in bottled water samples range from 22 particles per liter. Particle sizes ranging between 100 and 300 nanometer were dominant and accounted for approximately 31% in these bottled water brands. You may ask, what's the problem? Microplastics could pose problems that would likely infer alteration of viability or inflammation at the gut level, and long-term accumulation of it in liver tissues and lung tissues could lead to liver disease and chronic pulmonary disorders. Another issue that arises from microplastics is because of the additives added to the plastic polymers to modify their properties. These additives were reported to be responsible for oxidative stress, endocrine disruption, impaired lipid metabolism, and even cancer in many organisms, not just humans. By harnessing the concept of photochemistry, we'd like to propose a solution for this problem.
This project will help eliminate microplastics in bottled water and will therefore not affect the consumer's health.
We have utilized a very specific type of reaction, and that is the Photo-Fenton reaction. It is essentially the Fenton reaction but with added ultraviolet or UV light. In a typical Fenton reaction, ferrous iron under mild acidic condition is oxidized by hydrogen peroxide to form ferric ion, hydroxyl radical and hydroxyl ion. However, that ferrous ion is further oxidized into ferric ion and is hardly reversible as it will be chelated by oxalate anions. However, when UV light is present in the reaction, a miracle happens. Ferric begins its reduction process back into ferrous and breaks down water into hydroxyl radical and hydrogen ion. Not only that, UV light will also double the hydroxyl radical production. When iron 2 hydroxide is photoreacted to produce ferrous and hydroxyl radical. Essentially, UV light duplicates hydroxyl radicals like magic. But wait, why are hydroxyl radicals being emphasized here?
Well, they can be the demolition crew towards microplastic and nanoplastics too. Basically, hydroxyl radicals undergo an advanced oxidation process or AOP, where the radicals oxidize the microplastic completely, breaking them down into simpler carbon dioxide and water molecules. As you can see, this contraption here includes two different phases, the degradation phase and the decontamination phase. During the degradation phase, water passes through a cylinder that contains a UV lamp inside it. The water is then mixed with hydrogen peroxide and ferrous sulfate solutions, with the UV lamp acting as the UV ray supply for the Photo-Fenton reaction to occur. This is to ensure the hydroxyl radicals do their job completely by breaking down microplastic compounds. After all the degrading has been done, we need to decontaminate the water from the hydrogen peroxide. Sodium sulfide is added that reacts with the hydrogen peroxide to form sodium sulfate and water. Finally, sodium sulfate alongside the iron compounds are then removed by a semi-permeable membrane via a process that is akin to reverse osmosis. We hope this project achieves its purpose in removing microplastics and nanoplastics from bottled water and thus keeping the people's well-being safe. Thank you for watching.